Hi, and welcome to Calculus Examples. I'm Dr. Finch. Today we're looking at an example where we have an ellipse we are working with. I actually really like ellipses. I remember there was a phase at which I did pretty much the whole semester in ellipses, uh, everything ellipse. So much fun. So we have x squared over a squared plus y squared over b squared is equal to 1. So you'll notice it's almost like a circle. The only difference is we have these funky numbers, a squared and b squared, in the denominators all of a sudden, and ab are some positive numbers. We don't know what they are, but they're going to determine how kind of eggy our ellipse looks like. So here's a picture of it, right? We've got from negative a to a on our x-axis and from b to negative b on our y-axis. We're asked to set up and solve the integral that gives the area inside the ellipse. So what we're going to do to figure that out is we are going to write our equation in terms of y. And in particular, let's see, I'm going to actually draw this out. We're going to do just the top half. We're going to go from negative a to a, and then we are going to double that to give the entire area of the ellipse, which is going to make our lives a little bit easier there. So we're going to start off with our original equation, x squared over a squared plus y squared over b squared is equal to 1. And we want to solve this for y so that we can get this line right here, and that's the top of our ellipse. So that's going to describe the line that's going to help us get our area. We're going to start off by moving our x squared over a squared to the right-hand side of our equation. So we're going to subtract that from both sides. And next up, we're going to move that b squared. We're going to multiply both sides by b squared to get the b squared over onto the right-hand side as well, right? We want to isolate our y, so we want to shove everything over to the other side of our equation. Last thing that we are going to do is we are going to take the square root of both sides, which means we do need to take a plus minus. As you'll recall, when we do a plus minus, the plus square root is the top half of our ellipse, and the minus square root is the bottom half of our ellipse. So if we go up to the picture, when we talk about plus, it is this line here, minus is this line here. And the reason we have two different ones is because it's not a function, it's an equation. So we are going to do one more thing to make our lives a little bit easier. You'll notice that our b squared is multiplied by this whole junk, 1 minus x squared over a squared. And when we have square roots that are multiplied, we can break them apart. We can't do it with pluses and minuses. So like this 1 minus x squared over a squared, you can't break up that square root. It is set as is, but we can pull out that b squared. And if you take the square root of something that's squared, we're just going to get rid of that square root entirely. They're going to cancel each other out. So there is our equation that we're going to work with. We're going to use that equation to figure out our setup for our integral. Let's see, our area then is going to be, we said it was going to be twice we're going to go from negative a to positive a, and we're going to do the positive part of our equation there. So we're going to have 1 minus x squared over a squared dx. So there is the first part of our question that we were supposed to solve, and that is setting up the integral. And this part can be tricky in and of itself. There's a lot of algebra going on in that particular equation. And if you enjoy explanations like this, subscribe. I'll be doing Calc 2 problems all spring. All right, let's get down to the basics. Now we actually have to solve this sucker. We are going to have a little bit of an issue here. You'll notice that the tricky part of this is that we have this x squared over a squared stuck inside of our square root, which is going to make our lives a little bit more tricky. So what we're going to do is we are going to do a nice little u substitution. And we're going to use that in order to solve for our integral. So I'm going to go to the next page here so we have a little bit more room here. And we are going to take, let's do this. We're going to take u is equal to x over a. And you'll notice I didn't say x squared over a squared. And let me just rewrite this one more time. Notice we can rewrite this as x divided by a quantity squared dx. You'll see why we do this in just a little bit. So there is our u. Our du ends up being 1 over a dx, which means that a times du is our dx. Notice we do need to make that particular change right there because this a doesn't appear, we don't have a 1 over a dx. We just have a dx here. So we are going to need to make that change. Let's do a change of bounds as well so that we do not have to go back to x's before we are done with this problem. So our lower bound starts at negative a, which means our new lower bound is going to be negative a over a, which is negative 1. Oh, isn't that cute? And our upper bound is x is equal to a, so our new upper bound is a over a, which is a positive 1. Aw, and we're going to find out why that is so wonderful. All right, let's punch that all in. Let's see. This is going to give us 2. That just kind of comes along for the ride. I'm going to throw that b on the outside of our integral because we're not really moving it around as much. It's not doing anything. We're going to change our bounds from negative 1 to 1. And then we are going to have a square root 1 minus u squared times a du. And notice this a here actually can go on the outside of our integral because it's not doing anything else, right? 2ab integral negative 1 to 1 square root of 1 minus u squared du. All right, now that we have this, there should be alarm bells going off in your head when you look at this particular equation, right? 1 minus u squared under a square root should say something to you. And why don't I set that equal to y? This is different from the y that we had to begin with, but let's just set it equal to y. Let's square both sides. So we get rid of the square root and let's add our u squared to both sides. This equation should look familiar. Whenever you have 1 is equal to some number squared plus some number squared, that is a circle. And whenever we have a circle, we actually don't need to use calculus to find the area. We know the area of a circle. And in particular, this is going to be the top half of a circle. So our original circle area is equal to pi r squared. Top half of the circle area is equal to 1/2 pi radius squared. And in this case, what is our radius here? Our radius is going to be equal to 1. And we see that with our bounds right there. So this gives us 2ab times 1/2 pi times 1 squared. Now at this point we notice that the 1/2 and the 2 are going to cancel each other out. And we end up with a pi ab, or I'm going to rewrite that so it looks a little prettier. I'm going to do ab pi. And there is our solution for the area of an ellipse. I hope you really enjoyed this one. I love ellipses. They are so pretty. Thank you so much for listening.